All right, so today we're looking at a variety of models. We're going to focus today's lesson on the one that I want you to actually be able to come up with on your own. But I do want to address these other four as we look at it, okay? So we have exponential growth and decay, all right, which actually I should say these two are the type that you should be able to, or you will be able to actually come up with given certain data, all right? The other three, the Gaussian model, the logistic growth model, and the logarithmic model, okay, those are ones where I would like you to know those terms and know what the equations look like and know what the graphs would look like. All right, but I'm not going to give you data and say, hey, fit this into a logistical model. Okay, that's kind of beyond what we need to do with our study here. Okay, so we're going to come back to the exponential in a second, but I want to point out our logarithmic, logistic, and Gaussian models. Okay, so let's zoom in a little bit here. We have the logarithmic models. And this is one that we're actually familiar with because we had the parent function for logarithms, right? What did that parent function for logarithms look like?
The thing, it was like this thing.
Like the shape?
Okay, yeah, it looks like this, okay? It had what at x equals 0?
Asymptote.
An asymptote, okay, we have an asymptote at x equals 0. And then it comes up and it starts to kind of level off. It does continue to increase forever, but it increases much slower as time goes on. Okay? Notice it, remember it typically will, at least the parent function will cross at the point 1, 0. Okay? So those are our logarithmic models. Now, we also have logistic growth model. By the way, logarithmic models are pretty easy to identify. Because if you notice, they're the only ones that have logarithms in them. Okay? So, these ones should be easy to identify, at least what the equation goes with the term. But make sure you know what the graph would look like as well. Okay? Now, logistic models are kind of interesting because these models are used for situations where, say, we have some sort of growth, but the rate of growth kind of changes, and then over time it reaches kind of a maximum. Okay? For example, let's think about, a good example is like an epidemic that breaks out, okay? At first, how many people are sick?
Yeah.
Just one or two, right? And then how quickly does it spread at first?
Slowly.
Pretty slow. But once we reach a certain point in time, it starts spreading a whole lot faster because there are more people infected, they infect more people, and it's a snowball effect. But then one of two things happens. Either we reach the point where almost everybody is sick, or we have some kind of an intervention where people are starting to get better, or there's medicine being distributed, or something like that. So the spread of the disease slows down. Okay? That's what this model is actually, that's one of the applications this model is used for. We have slow growth at first, then it shoots up, and then it starts to level off. Okay? There actually is an asymptote at the top of this one at whatever the capacity would be. So like if we were talking about an epidemic running through our school, okay, whatever the total number of people in our school would be is where our asymptote would actually be. All right? And theoretically, we'd never reach the point where 100% of our people are sick. Okay? Theoretically. But this can be used for epidemics, but also can be used for like the growth of a city. okay, at some point you're going to reach the point where your city just simply can't hold any more people. All right? So at first you may have a real small town, but then it gets popular and people start moving there, and as people move there, it becomes even more popular, more people hear about it, and then the population really booms, but then it starts to fill up and people are like, I don't want to go there because it's crowded. So it's it may still grow, but it's going to slow down a lot. It's the same kind of model here. Okay? So that's what a logistic model looks like. Okay? The key feature for this equation is that you have a binomial in the denominator that has an exponential as part of it. Okay? You have a binomial in the denominator that has an exponential that's part of it. And that exponential will typically have a negative in there. Okay? That's what causes it to level off, actually.
Wait, is that E like E, or is it just a variable?
No, that's the number E. Yeah. Because it is a continuous type of growth model. It's just not exponential growth. It's a logistic growth. Mm-hmm.
So when you write the parent functions or like the variable form of the equation, it always is written with natural logs, so E, and can't be written with like logs with a different base.
I think theoretically we could have different bases. Yeah, like just like exponential growth. We looked at like compound interest and stuff. It could have a different base other than E, but this is the most general, most common form, I should say. All right, and then we have the Gaussian model, okay? As you look at the equation, the key feature of this equation is, notice E is raised to this big old power. E is to the negative x minus b squared over c. Okay? The key feature in this is that you have an x squared in the exponent. Okay? X squared in the exponent. All right? Now, this model we actually have already used before. We looked at the equation actually very, very briefly.
Where?
But you used this shape back in our statistics unit.
So it's the bell curve one?
It's the bell curve, okay? The Gaussian model is actually the bell curve, okay? So when you see a bell curve, that's a Gaussian model. So here we go, just to sketch one so we remember. Here's our bell curve. Okay, that's decent. Okay. All right. So we're going to revisit these three models on Monday and look at using them in a couple of applications. You're not going to have to write those. But I do want to take some time looking a little more closely at the exponential growth and decay for today. Okay? First of all, just a reminder here of what our exponential looks like. Okay? The growth obviously is going to be increasing. Okay? Notice here, the decay is when our exponent is negative, okay? Which makes sense, because what does multiplying x by a negative do to our graph?
1 over that.
Makes it a fraction.
1 over that.
Well, that's the exponent negative makes it the reciprocal, but what did you say?
Reciprocal.
Fraction.
Okay,
The
think about the graph. What does it do to the graph?
it reflects it across the y-axis.
Yes, remember making x negative reflects our graph across the y-axis. That's why here we're crossing at 0, 1 and it's increasing. Okay, that's our growth. But over here we have now reflected that across the y-axis. So we're still hitting at 0, 1, but now it's decreasing. Okay? So that's what that looks like. Now, here's one real simple example to start with here. We have an estimate of the world population. This model here estimates the world population in millions. That's one thing that's a little bit tricky with this one. It's in millions from 1998 through 2007, okay? So when I see 1998 had 5,930 millions,
Wait,
what is that actually?
5,930,000,000.
Why wouldn't they just put
Yeah, it's about 5.93 billion, okay? So, do be careful with units of measure on these types of things. But the nice thing for us is that for this example, the model has already been given, okay? And notice our domain is for t equals 8 to 17 because our model went from 1998 to 2007. So they're using 1990 as our 0 again, okay? That's something to keep in mind. So t equals 0 is 1998 or 1990, okay? Now it says, according to this model, when will the world population reach 6.8 billion? All right, so what are we plugging into our equation?
6,800.
Yes, 6,800, because 6.8 billion is 6,800 millions. All right? So that equals 5,400 e to the 0.011852 t power. And especially when you're given it in a model, do not round. Okay? Don't round what you're given at all. Okay? So, of course, we'll divide, and then after we divide by 5,400, how do we solve? ln, okay? So e to the 0.011852 t is whatever 68 over 54 is. And we're going to take the ln of both sides. Okay? Yeah, 6,800 over 5,400. Okay. So what does that end up equaling? ln of 68 over 54? Sorry, I'll blow that up for you. .2305. So then we divide that by the 0.011852, and what does t equal?
That divided by what? 0.01182 is 19.45.
Okay. So,
Which
what?
adds up since it's off the graph.
So do we have to start with the year 1998 minus 8? 1990?
Yes, we have to remember that 0 is at 1990. So what year would this be?
This would be
2009.
Okay.
Yeah, and a little bit more, so like halfway through.
Yeah, this would be sometime between 2009 and 2010, if you wanted to say that. Okay? June. Something like that. So, sometime. Oop.
19.
Sometime in 2009 to 10. Okay? All right, so that's a pretty straightforward application. Okay? You're just plugging it in. If you really wanted to, you could put the two sides of this equation into your calculator and find the intersection point. You know, if you're having trouble solving it algebraically, but these ones you should be able to solve algebraically pretty easy. Okay?
So
All right, any questions?
Not so.
All right, so let's get to the part of this that is where the real work comes in. The nice thing about it is, though, we've done this before, just in a very different context. All right, so now we have the only type of model that I actually expect you to be able to come up with from data, and that is the exponential growth or decay model. Here we have in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies. And after 4 days, there are 300 flies. How many flies will there be after 5 days? Now, the model we're dealing with, remember the basic form of the model is this y equals a times e to the bt. A in our model is going to be the starting amount. And we saw this actually when we did our exponential growth with compounding continuously. That was our principal amount, the starting amount. B is actually going to end up being our rate of growth or decay if it's negative. All right, so we have that, and we need to realize what we're really being given, okay? First of all, understand the independent and dependent variables in our equation. The independent variable is our time, the number of days, okay? And the dependent variable is y, which is the number of flies, okay? So we're given 2 points here, the point 2, 100, and the point 4, 300. So now that we have these 2 points, we can use our model and actually write 2 equations. One, we can use 100 for y, and we'll use the 2 for t, so it's a times e to the b times 2, or 2b power. And then for our second point, it'll be 300 equals a times e to the 4b power. Okay? So now we have 2 equations and 2 variables. So we have to solve this. And there's 2 different ways that you could do this. It's really a matter of preference. It's not that one's right or wrong or even better or worse than the other. One method is going to be if we take one of these equations and we solve it for a, let's say we divide both sides by e to the 2b, we'll get a equals 100 divided by e to the 2b power. And then what we can do with that is plug that in for a in our other equation. So we'd have 300 equals 100 over e to the 2b power times e to the 4b power. Okay? So at this point, we would reduce. Anytime you're dividing and have the same base, you subtract the exponent. So that would be e to the 4b minus 2b. So that's e to the 2b power times 100 equals 300. Okay? So of course we'll divide by 100. That's e to the 2b. And now's the point where we can take the natural log of both sides. Okay, ln, that undoes that, so we're down to 2b equals ln of 3. And of course we just divide by 2. So b is 1/2 of ln of 3. All right, and you can punch that into your calculator. And that is 0.549306, I believe. All right, so at this point, then we need to figure out what a is. Well, the nice thing is we've already solved for a up here, so we can just plug 0.5493 into b and that'll give us A. So let's do that here. A is 100 over e to the 2 times 0.5493 power. And that actually ends up giving us 33 1/3. If you don't round at all through the whole thing, it'll give it that exactly. Okay? So our model in this case is going to be y equals 33 1/3 times e to the 0.5493 times t power. There's our model. And if we're trying to figure out how many flies there were after 5 days, all we have to do is plug in 5 for t. So 33 1/3 times e to the 0.5493 times 5 power. And we get 519.6 and change. So we've got 519 or 520, 519 to 520 flies after 5 days. Okay? So there's our solution. Now, I want to take a step back for just a moment here because I told you there's an alternative way of solving this system. Okay, so let me just show you that real quickly here and then we'll be done. Okay? The alternative way is actually to set up a proportion. So I'm going to put A times e to the 4b over A times e to the 2b. And that's going to equal 300 over 100. Okay? So notice I put this over this, and that's going to equal this over this. The nice thing about this method is I actually get to this part right here really fast. Okay, and you can see that here because the a's will cancel. I have division, so I'm going to subtract the exponents. I have e to the 2b, and then 300 over 100 is 3. At this point, everything after this is the same as what we had down here. Okay. So we get to this point a little bit faster. If you like to do it that way, if not, great. Just do whichever way is most comfortable to you. All right, so one more example here of finding an exponential model. We have a colony of bacteria growing at an exponential rate. Obviously, bacteria are going to grow constantly, not at a certain rate per day or something. On day 2, there are 78 bacteria present, and on day 5, there are 650 bacteria present. So it's growing pretty rapidly, it seems. Okay, so we have here our 2 points. If we remember, we're going to get 2 points. On day 2, we have 78 bacteria. Notice here that we're going to use t for our number of days. And then we're going to let y be the number of bacteria. That's our dependent variable. Okay, it's going to grow as the days change. All right, so we have points t, y here. So our first point is 278. Our second point is going to be 650. All right. So let's remind ourselves here, the exponential growth model is y equals a times e to the bt power. All right, so we're going to plug in the t's and the y's to come up with 2 equations. So here we have 78 equals a times e to the 2t power. And then we also have 650 equals a times e to the 5t power. All right, now we had looked at 2 different ways of solving this system. Now that we have a system of equations, we got to solve for, well, I'm sorry, it's not 2t, oops. It's not 2t and 5t, it's 2b and 5b. All right, so let's replace those with b's like they should be. So we plugged in 2 and 5, 4t. Alright, so let's solve this system. I'm going to use the proportion method just because that's the one I prefer. A, e to the 5b. I always put the bigger exponent on top so it reduces nicely. A, e to the 2b is on the bottom. So since 650 corresponded to day 5, it's going to go on the top on this side, and 78 is on the bottom on this side. Alright, so there's our proportion. We do this because now the a's cancel, and this is e to the 3b power equals 650 over 78. So now we can take the natural log of both sides, and we get 2.12 if we plug that into our calculator on the right. On the left, the natural log undoes the exponential, so we just have 3b. And of course we then need to divide by 3, and we get 0.7065 and some more decimals as well. Alright, we'll leave that whole number in our calculator as we go to find A. Alright, so now we know that our model is, we'll kind of fill it in as we go here, y equals something times e to the 0.7065 t power. Alright, so now we just need to figure out what that value of a is. So to do that, we're going to take this, and I'll use the 78 equals a times e to the 2b, and now instead of b we know that that is 0.7065. Okay. So all we need to do at this point is divide both sides by e to the 2 times 0.7065 power, and we get 38.47. Okay, so now we can fill that into our model. 38.47 e to the 0.7065 t power. That is the model that we're looking for.